Right now, an AI language model is choosing its next word. Out of roughly 100,000 possible tokens, it needs to pick just one. But it doesn't simply pick the most likely option. It rolls a weighted die, and there's a single number that controls the shape of that die: temperature. Turn it down, and you get safe, predictable text. Turn it up, and you get creative, surprising, sometimes unhinged output. The mathematics behind this dial is called Softmax, and it's surprisingly elegant. The simplest decision an AI can make is yes or no. You might think of a step function, 0 below the threshold, 1 above. But there's a fatal flaw. At the threshold, the function jumps. It has no derivative, and without a derivative, backpropagation cannot flow. The solution is the sigmoid function. Sigma of z equals 1 over 1 plus e to the negative z. It's a smooth switch that glides continuously between 0 and 1. At z equals 0, sigma is exactly 1/2, the perfect coin flip. As z increases, the output approaches 1. As z decreases, it approaches 0. Sigma of 2 is 0.88, quite confident. Sigma of 5 is 0.99, almost certain. Sigma of -2 is just 0.12, almost certainly no. And here's the beautiful part. The derivative of the sigmoid is sigma times 1 minus sigma. The function describes its own rate of change. This bell-shaped derivative peaks at z equals 0 and vanishes at the extremes, meaning the sigmoid is most sensitive right at the decision boundary. So we can interpret the sigmoid output directly as a probability, the probability of yes. Distinguishing cat from dog is a start. But what if there are 4 options: cat, dog, bird, or fish? A neural network's final layer outputs raw scores called logits. Here they are: 2.0, 1.0, 0.1, and -1.0. The problem is clear. Some scores are negative and they don't add up to 1. These aren't probabilities. Step 1. Exponentiate. Raise e to the power of each score. This makes every value positive. Step 2. Sum them all up. 7.39 plus 2.72 plus 1.11 plus 0.37 gives us 11.58. Step 3. Divide each by the total. Now every value is between 0 and 1, and they sum to exactly 1. We have a probability distribution. This 3-step process is the Softmax function. The network says cat with 64% confidence, dog at 23%, bird at 10%, and fish at just 3%. 3 key properties. All values are positive, they sum to 1, and larger logits gain exponentially more weight. Softmax has one more hidden parameter. Instead of computing e to the z, we compute e to the z divided by t, where t is the temperature. When t equals 1, we get the standard softmax we just saw. But watch what happens when we change the temperature. Turn the temperature down towards 0, and the highest scoring option dominates completely. The distribution becomes a spike. Turn it up, and all options become nearly equal. The distribution flattens out. Let's see all 3 side by side. At t equals 0.1, virtually all probability concentrates on the top scoring class. At t equals 1, it's a balanced distribution. At t equals 10, it's almost uniform, nearly random. This is exactly ChatGPT's temperature setting. Set temperature near 0 for a customer support chatbot. Safe, consistent, predictable. Set it near 1 for creative story writing. Surprising, diverse, sometimes wild. One number controls the entire spectrum from robotic certainty to creative chaos. If Softmax gives us probabilities, why not just pick the word with the highest probability every time? Consider the prompt. The weather today is blank. Sunny has 40%, beautiful 25%, unpredictable 15%. With argmax, you always pick sunny. Run it 3 times. Sunny, sunny, sunny. The same input always produces the same output. Predictable, robotic, boring. But with probabilistic sampling, you roll the weighted dice. Run 1 gives sunny. Run 2 gives beautiful. Run 3 gives unpredictable. Same prompt, different results every time. Think of it like dropping a ball into probability-weighted slots. The wider the slot, the more likely the ball lands there. But it's never guaranteed. In practice, temperature near 0 for customer support, consistent and reliable. Temperature near 1 for creative writing, diverse and surprising. The Softmax distribution is the shape of the die. Temperature controls how loaded it is. The model now outputs probabilities. But what makes a good prediction? The correct answer is cat. Prediction A puts 90% on cat. Confident and correct. The loss is negative log of 0.9, which is just 0.105, a tiny penalty. Prediction B puts only 40% on cat. Ambiguous, hedging its bets. The loss jumps to 0.916, 9 times larger. Prediction C puts 97% on fish and just 1% on cat. Confident and completely wrong. The loss explodes to 4.605, 44 times the penalty of prediction A. The pattern is clear. The loss is negative log of the probability assigned to the correct class. The general form is called cross-entropy. H equals negative sum of yi log I hat I. When the label is 1 hot, only the correct class survives, and it simplifies to negative log of the correct probability. The intuition is powerful. Negative log punishes confident mistakes catastrophically. This is what teaches the model humility. And this loss is exactly what flows backward through backpropagation, the gradient that updates every weight in the network. Let's look at this loss function more closely. This is negative log p, plotted from 0 to 1. At p equals 1, a perfect prediction, the loss is 0. At p equals 0.5, a coin flip, the loss is 0.693. But watch what happens as p approaches 0. The curve doesn't just rise, it explodes upward, a vertical cliff. At p equals 0.01, the loss is already 4.6. At p equals 0.001, it's 6.9. This creates two zones. A safe green zone where p is above 0.5, and a red danger zone where p is below 0.1. And here's a remarkable pattern. Going from 0.9 to 0.1 adds about 2.2 in penalty. Going from 0.1 to 0.01 adds about 2.3. On a log scale, every 10-fold decrease in probability adds the same fixed penalty. Now, the most surprising result of this episode. When you combine Softmax with cross-entropy and compute the gradient, you get this. The partial derivative of the loss with respect to each logit is simply y hat I minus yi. The prediction minus the truth, that's it. No complicated expressions. The entire gradient is just how wrong each prediction was. Let's zoom out and see the complete picture. Every time an AI learns, it runs a cycle with 6 steps. Input data, represented as vectors and matrices, which we covered in episode 1. A forward pass through the computation graph, episode 4. Softmax converts raw scores into probabilities. That's today. Cross-entropy measures how wrong those probabilities are, also today. Backpropagation sends the error signal backward, episode 4 again, and gradient descent updates every weight, episode 2. Then it loops back to the beginning with the next batch of data. Today's 2 new pieces, Softmax and cross-entropy, sit right at the heart of this pipeline. Softmax turns computation into decision. Cross-entropy measures the quality of that decision. And episode 3's Bayesian thinking is hidden here too. Weight decay, L2 regularization, is mathematically equivalent to a Gaussian prior on the weights. GPT processes trillions of tokens. Each token prediction is one revolution of this cycle. 5 episodes, and we've covered the mathematical foundation of modern AI. Let's bring it all together. Today we learned 4 ideas. The sigmoid, a smooth switch between 0 and 1. Softmax, turning raw scores into a full probability distribution. Temperature, one number that controls the spectrum from certainty to creativity. And cross-entropy, a loss function that catastrophically punishes confident mistakes. In episode 1, we learned how AI represents the world as vectors and matrices. In episode 2, how AI improves, gradient descent. In episode 3, how AI handles uncertainty, Bayes' theorem. In episode 4, how AI learns from mistakes, backpropagation. And today, how AI makes decisions, Softmax and cross-entropy. In episode 6, we'll discover why neural networks can learn almost anything, the universal approximation theorem.